Hello and welcome to today's lecture on switching power dissipation. We have discussed various types of MOS circuits in a bottom up approach. Using a bottom up approach, we started our discussion on MOS transistors, various characteristics of MOS transistors. Then we discussed about the realization of different types of MOS inverters using MOS transistors. After that, we have discussed different types of combinational circuits that you can realize using MOS transistors. We have discussed gate based logic circuits like static CMOS, dynamic CMOS, and also switch based logic circuits like pass transistor logic. Then we have covered the MOS memory devices, and finally in the last lecture we have discussed about finite state machine. So, that gives you a complete background of different types of MOS circuits that you will encounter in your VLSI circuits and systems. In other words, now this stage is ready to discuss about low power aspects, and today we shall start with our discussion on sources of power dissipation. First lecture will be on switching power dissipation. That means, that is one of the most important component of the sources of power dissipation. So, here is the agenda of today's lecture. First, I shall give a brief introduction about types of power dissipation, then discuss about the classification of sources of power dissipation, dynamic power, and there are three components, as you know: switching power, short circuit power, and glazing power. And also there is another type of power dissipation, that is called static power dissipation, that we shall discuss later. But based on this dynamic power, what are the degrees of freedom, that I shall discuss maybe at the end of our discussion on different types of sources. In this lecture we shall focus on switching power dissipation. But before I do that, let us discuss about what do we really mean by power, and what are the different types of power dissipation that we encounter in digital circuits. One of the most important sources of power dissipation, rather important power dissipation, is peak power. So, what is peak power? Peak power. If you plot the power dissipation of a circuit over a period of time, this is the power which is a function of time, you will find that it is not constant. So, sometimes it is more, sometimes it is less, and so on. So, it will be somewhat like this. So, it is a function of time. You may be asking why this kind of peak, maximum power occurs. It occurs in many situations. For example, when you are turning the power of a laptop or a computer, then at that point it will consume large power. You may be asking how the peak power, which is essentially the instantaneous maximum power that is drawn from the power source, how it affects the behavior of the circuit. Actually, whenever there is a surge in power dissipation, that means suddenly it increases, lot of current flows through the power lines. That means, power is drawn from the supply line, and also that current passes through the ground. So, the supply and ground lines, through those lines heavy current will flow suddenly, and because of that it will lead to some kind of transients on different parts of the circuits. That means, it will affect other components of the circuits. That means, it will lead to glitches, it will lead to droops, and so on. That means, as a consequence of this peak power, sudden surge of power drawn by the circuit, some bits of a computation may be erroneous. That means, some, or whenever you are writing or reading from memory, you may be reading wrong data when that transient occurs. So, in other words, peak power affects the circuit in terms of correct output. That means you may not get correct output. In other words, reliability of the circuit is affected. So, this is the peak power. Then second one is the average power. What is the meaning of the average power? For example, for this particular waveform, the average power will be somewhat like this. So, maybe it will be like this. This is the average power. So, this is average over a period of time period, say t. So, if you average it over a time period t, then this is the power dissipation. In what way this average power is important? In fact, the average power is very important from the viewpoint of packaging and cooling cost. That means, the power dissipation over a period of time, that has to be dissipated using the cooling and packaging arrangement. So, the packaging and cooling cost is affected by the average power. Not only that, the average power affects the cost of the battery, because you are drawing the power source from the battery, or it may also affect the power circuits, for example, regulated power supply, transformers which are used to generate the DC power. So, those will be affected, rather the weight of the system, volume of the system, and the packaging and cooling cost, these will be affected by this average power dissipation. So, average power is very important from whenever your circuit is operating from battery, because the size of the battery will be large, and it will not last for a long duration if the average power is high. However, whenever you reduce the average power, the peak power is also reduced. That is the reason why most of the time we shall be focusing on average power, reducing the average power, and simultaneously the peak power will be reduced. Now, here for example, the power in watts is plotted, and P1 is the peak power for a duration of time, say T1, 0 to T1, and similarly average power dissipation P2 is for another duration, maybe T2. So, that means that this peak power dissipation at this moment and at this moment may be different. I mean, average power dissipation at during the time T1 or during time T2 may be different. Now, there is another very important concept, that is energy. Power and energy, these two are, although they are different, sometimes we use them interchangeably. In what way they are related, let us try to understand. What do we really mean by energy? Energy is the actual energy what is drawn over a period of time from the power source. That means, it is power into time, that is your energy. For example, in this particular plot we have that power dissipation was P1 and over a period of time T1. So, E1 is the energy which is represented by the area under this rectangle, area of this rectangle. So, that means this energy, say if this is the power dissipation P1, average power dissipation P1 over a period of time T1, and say another power dissipation which I have shown, that is average power dissipation P2 over a time period T2, then energy here obviously time and here P. So, energy E1 is the area of this rectangle. Similarly, the area of this rectangle is this your again E2 is area covered by this rectangle. That means, energy E1 is equal to P1 average power dissipation into T1. Similarly, E2 is equal to P2 into T2. Now, you may be asking in what way energy affects your circuit. Particularly for battery operated systems, energy is very important, because whenever battery is fully charged, some amount of energy is transferred from the charging source, and that energy has to be used by the battery for performing computation and other thing. So, you have to essentially minimize energy whenever you think about battery operated systems. That means, whenever we say low power, essentially we are meaning low energy, but sometimes we use these two interchangeably, although they are different. So, we have discussed about different types of power dissipation and relationship between power and energy. Now, let us focus on the sources of power dissipation in CMOS circuit. The sources of the different sources can be divided into two basic categories, dynamic power and static power. So, what do you really mean by dynamic power? Dynamic power dissipation occurs when the circuit is in operation, when the circuit is in action. You have applied a supply voltage, you have applied clock, you are changing the inputs, outputs are changing, that we call the circuit is in operation or in action, and that time whatever is the power dissipation we call it dynamic power. On the other hand, static power dissipation is when maybe the inputs, I mean the power source is there, but inputs are not changing, clock is withdrawn, then we call it static power. And static power dissipation, as we have seen in case of CMOS circuits, it is essentially leakage power dissipation. So, and again the dynamic power has got three components which I mentioned in my first lecture. The three components are switching power, short circuit power and glitching power. So, these three different types of power dissipations occur when the circuit is in operations and which are categorized as dynamic power, and switching power is the most important component which I shall discuss in this lecture. What do we really mean by switching power and why it occurs? Switching power occurs due to charging and discharging of load and parasitic capacitors. As you have seen in a CMOS circuits, there are lot of capacitances, gate capacitance, drain capacitance, interconnect capacitance and so on. Various types of capacitance are present in a circuit, and those capacitances gets charged and discharged during normal circuit operation, and that leads to power dissipation, and that is known as the switching power dissipation. And let us look at a CMOS circuit. We have seen the basic the generic schematic diagram of a CMOS circuit is like this. You have a pull up network made of NMOS PMOS transistors, and you have a pull down network made of NMOS transistors, and we have a load capacitance CL, that is how we model it. Although CL is shown as a lumped capacitance, it is essentially comprises many capacitances including gate capacitances, interconnect capacitances and various other types of capacitances. Now, in this situation, how the switching power dissipation occurs? Now, let us see how it is occurring whenever the output is changing from say 0 to 1. Let us consider a very simple circuit, say an inverter. You have an inverter for the sake of simplicity, and this is connected to VDD and this is connected to input. Now, you have a load capacitance CL connected here. Suppose initially the input was 1 and it had changed from 1 to 0 input V in. What will happen to V out? V out will change from 0 to 1. Then what will happen? That means initially the charge across this capacitor, charge that was stored in this capacitor was 0. Now, it will charge through this transistor, because when the input voltage is 0, that time this is off and this is on, and as a consequence this capacitor will charge through this PMOS transistor. Through this PMOS transistor it will charge, and this while it charges, some power will be dissipated in this PMOS transistor because it is a resistive component, and out of the total energy that is drawn from this power source, maybe battery or some power supply, some will be lost as in the form of heat, because when current passes through a resistive load, the that power dissipation gets dissipated in the form of heat. On the other hand, part of the energy will be stored in this capacitor CL. Later on we shall see what is the energy that is drawn from the battery for charging a capacitor and how much energy is stored in this capacitor. Now suppose it changes from it changes now from the same circuit. Now the input changes from V in now changes from 0 to 1. Then what will happen? Then what will happen? This will become off and this will become on, and as a consequence, as I told, some energy was stored in this capacitor. That energy, that charge energy means that will be stored in the form of charge, that will get dissipated through this NMOS transistor. That means the energy that was stored in this capacitor while after charging from VDD, that will now get dissipated through this NMOS transistor, and now the charge will become 0. That means whatever energy that was drawn from the power source, part of the energy is dissipated while charging, and part of the remaining part of the energy gets dissipated while discharging. That means when the output goes from 1 to 0, as it is shown in this diagram. So this is the charging current. So for a general CMOS circuits, the pull up network is responsible for power dissipation while charging, and pull down network, which may be a complex network, that is responsible for power dissipation while discharging. So from the capacitor it gets discharged through the pull down network. Now we can calculate the power dissipation. Let us now proceed to calculate the various power dissipation that occurs in a circuit in this type of circuit. So how much energy is drawn? So during transition from 0 to 1, how much energy is drawn from the power source? Let us find out that. So energy drawn E 0 to 1 is equal to 0 to VDD. This capacitor is charging from 0 to VDD, and power dissipation and time, that time over a period of time this is happening. And as you know, current will pass through this part of the circuit, and that will lead to power dissipation. And what is the expression for current? This current is not fixed, that current will be equal to IT, and this will vary with time, CL into dV0 dt. What is dV0? dV0, V0 is the output voltage. So rate of change of output voltage with time into the into capacitance value, say load capacitance, is the instantaneous current that will be passing through this part of the circuit. So if we substitute it here, then we shall get CL will come out, this will become 0 to VDD into that dV0 VDD. So we shall dV0 dt 0 to 1 VDD, and it will be CL, energy is the 0 to VDD and CL dV0, and this will be equal to energy P, power is voltage into current, that we have missed here. So there will be a VDD factor. Pt is equal to Pt is equal to IT into VDD. This is the power dissipation. So, VDD will be factor when here. So, this if we evaluate, this will become CL VDD square. So, CL VDD square is the energy that will be drawn from this power source. So, we find that an energy of CL VDD square will be drawn from the power source. Now, you may be asking, for different types of the charging current, will this expression be same, or in other words what I am telling, suppose you charge is using a constant current source, from a constant current source, will it be same whenever we do it through a resistor as we have done in this case? Actually, as the capacitor is charged from 0 volt to VDD, this energy will be same irrespective of the way you charge it. That means, the nature of charging current can vary like this, as it happens in whenever you charge it through a resistor, or it may be a linear current will fall over a period of time when it charges to VDD. So, irrespective of that, this will be the energy that will be drawn from the power source. So, that is the reason why there is no other parameter or factor. Now, out of this energy, how much is actually stored in the capacitor and how much is gets dissipated in that load resistance. Load resistance in this particular case is PMOS transistor network. So, let us calculate that. That means, the energy that is being stored in this capacitor EC will be equal to, then let us consider the time taken is 0 to t is V0 IT into dt. V0 is the output voltage, which is also a function of V0, and current, that is IT and dt. So, this we can write as 0 to VDD. If we substitute IT here, it will become CL V0 dV0, because this dt will cancel, IT as we have seen is equal to CL dV0 dt. So, this dt and this dt will cancel out, we shall get dV0. So, if we evaluate this, we shall get half CL VDD square. So, we find that energy that is being stored in the capacitor is half CL VDD square. That means, out of CL VDD square, that the energy that was drawn from the power source, half of it is getting stored in the capacitor, that is being stored in the capacitor, load capacitance, and remaining half CL VDD square gets dissipated in the PMOS transistor network, or it can be a single PMOS transistor in the case of an inverter. Okay. And this remaining half of energy will be dissipated whenever the output switches from 1 to 0. So, we find that half of the energy that is drawn from the power source gets dissipated while charging the capacitor to raise the voltage from 0 to 1, and remaining half is getting dissipated when the output is switching from 1 to 0. Okay. Now, there may be some situations where if we apply a square wave to the input of a circuit. For example, we have an inverter. This is an inverter, and here we have applied a clock instead of any input. Obviously, in each cycle the output will charge, it will, so when the input is 0, output will be 1, and when it is output is 1, it will be 0. That means, in each cycle charging and discharging will take place. So, that means, whenever you have applied a clock, or in other words, when the output changes in each cycle of a clock, then what will be the power dissipation? So, power dissipation PD will be equal to 1 by T, because 1 by T is the time of this period, energy was CL VDD square. So, over a period of time T. So, whenever you calculate power dissipation, it will be 1 by T into CL VDD square, or that is equal to CL VDD square into F. In other words, the power dissipation will be equal to the clock frequency, proportional to the clock frequency. So, CL VDD square F, that is the power dissipation that will take place. Now, you see, in addition to power dissipation in the load, we may consider a circuit like this. Let us consider a simple NOR gate. So, in this, in addition to these inputs A and B, we have got, so we have got another node, this is CL, and here say node A, or you can say intermediate node, say CI. The capacitance here is CI, C1 and node 1, let us assume. Now, whenever this particular node is charging and discharging, it may so it will what will happen, this capacitor also will charge and discharge. However, in this particular case, the switching will not be from 0 to VDD, because as you know, whenever the charging takes place through a NMOS transistor, it can charge up to VDD minus VT. So, as a consequence, the power dissipation, that means energy that will be drawn, will be equal to VDD into C1 into VDD into VDD minus VT, because it will charge, it will not charge up to VDD, but it will charge up to VDD minus VT. That means, in this expression what we got here, this dV0 will not charge from 0 to VDD, but it will charge from 0 to VDD minus VT. So, as a consequence, you will get here CL VDD into VDD minus VT. So, you will be getting the power dissipation in an internal load, that will not be CL VDD square, but CL VDD into VDD minus VT. Now, okay. So, this is what will happen. Now, let us consider another very important concept, that is the switching activity, probability that the output will be 0 and how the will be 1. I mean, when the output will be 0 and when the output will be 1. Why this is necessary? Let us try to understand. You see, whenever we are considering a circuit, say NAND gate, will the output change in each and every clock cycle? It will not change. The output will change depending on the functionality of the circuit. So, we can calculate the probability of transition to 0 and 1 and find out the find out a parameter known as switching activity. In this particular, whenever we derive this expression, we assume that there is transition at each and every cycle, but that will not happen, because we are not really applying a clock to a circuit. It is a complex function, depending on the nature of the inputs, output will change, and so this will not change in each and every clock cycle. So, to take into account, we have to take another factor which is known as switching activity. Switching activity. What is switching activity? Switching activity is represented by alpha. How can you calculate switching activity? Switching activity is defined as probability of transition from 0 to 1, and this is equal to P0 into P1. What is P0 and P1? P0 is actually the probability that a circuit will remain will attain a value 0, and what is sorry, P0 is the probability that a circuit will attain a value 0, and P1 is the probability that a circuit will attain a value 1. Say let us consider the NAND gate that I have drawn. We know the truth table, say A, B, and say F for 0 0 0 1 1 0 1 1. So, output will be 0 only for 1 1, and for all the other 3 conditions the output will be 1. When any one of the input is 0, output will be 1. Now, what is the probability of this output to have the value 0? We can find out that there are 4 possible possibilities. So, out of 4 possibilities only once it can happen. So, in this particular case the P0 will be equal to 1 by 4, and what is the value of P1? Out of 4 combinations, 4 possibilities, input possibilities, the output can have the value 1 3 times out of 4. So, probability is 3 by 4. That means, if we take this over a long period of time, the switching activity or probability of transition from 0 to 1, 1 to 0 will be equal to this 1 by 4 and 1 by 3, and this will be equal to 3 by 16. That means, the switching activity will be 3 by 16, and this is the case for a NAND gate. We can generalize it. Suppose P0 is the probability that the output will have the value 0 is equal to say n0 by 2 to the power n. N0 is the number of zeros in that truth table. You see, we will write a truth table, number of zeros in that truth table by the total number. So, that will be equal to n0 is the total number of zeros by these are the total number of combinations. So, if P0 is equal to n0 by 2 to the power n, and P1 will be equal to n1 by 2 to the power n, and obviously n1 will be equal to 2 to the power n minus n0, because they are related. When the output is 0, it cannot when the output is not 0, it will be 1. So, therefore, P 0 to 1 for a general Boolean function can be written as n 0 by 2 to the power n into 2 to the power n minus n 0 by 2 to the power n. So, that is equal to n 0 into 2 to the power n minus n 0 by 2 to the power 2 n. So, we find this is the probability of transition from 0 to 1 and 1 to 0. So, we can say this is the switching activity. Now, for different types of gates the value will be different. For inverter it is 1 by 4. How it is 1 by 4? Because in an inverter, as we know, you have got only one input. So, probability that the output will be 0 is half, and probability that the output will be 1 is also half. That means, P 0 to 1 for inverter is equal to 1 by 4, and for NAND and AND gates we have already discussed, it is equal to 3 by 16. Similarly, for NAND and NOR gates it will be 3 by 16. However, for 2 input XOR gate it will be 1 by 4. Why so? Because in case of XOR, exclusive OR gate, say A and B are the 2 inputs, and this is the function of XOR. So, 0 0 0 1 1 0 1 1 exclusive OR, that means when it will be when the output will be 1, it will be 0 here and it will be 0 here, it will be 1 here, it will be here. So, output is has got 2 zeros and 2 ones. That is the reason why you are getting P0 is equal to 2 by 4 and P1 is equal to 2 by 4. Therefore, P0 to 1 will be equal to 1 by 4, half into half. So, we find for exclusive OR gate it will be half. Now, let us consider how the the switching activity changes with the increase in the number of inputs. As the number of inputs is increasing, how it will change? We can see for an XOR gate, as you increase the input, it remains equal to 1 by 4, that is 0.25. Why so? Because we have seen in the truth table always it will, the number of zeros and number of ones will be same, and that will be half of the total number. So, this value will be always equal to 1 by 4 XOR as you increase the fan-in number of inputs. On the other hand, for NAND and NOR and OR gates, it will change over time. You can see the expression that we got is this. So, n 0 into 2 to the power n minus n 0 by 2 to the power n 2n, and this expression as n increases it will reduce, because this factor is more, I mean this will increase, this will have larger value compared to this. So, we find that for fan-in is equal to 2, this is little more than, little less than 0.2, that is 3 by 16, and then it will become close to 0.1 for 3 input, and in this way it will reduce. What message does it give? Is there any message that we are getting from this? That means the switching power dissipation of a gate will be less if the fan-in is more. That means the power dissipation of the gate on the load capacitance charging and discharging will be less if the fan-in is more. Later on we shall see what impact it has got in the realization of a circuit, particularly whenever you go for low realization of low power circuits. Now, so far we have seen how it happens in case of simple gates, AND gate, OR gate, NAND gate, NOR gate and so on. But unfortunately, in our real life the gates will not be as simple as this, it will be more complex. So, whenever it is a complex gate, then we cannot really calculate the way we have found. So, for a complex gate the switching activity depends on two factors, the topology of the gate and the statistical timing behavior of the circuit. So, these two will affect the switching activity of the circuit. So, let us now define switching activity for a complex gate and find out an expression for it. Let Nn be the number of inputs, number of 0 to VDD output transitions. These are the number of output transitions that will occur in a circuit, and in the time interval in the time interval 0 to n. That means, out of n possible transitions, Nn is the number of transitions that is occurring from 0 to VDD. So, total energy drawn En will be equal to, we know for each transition the from 0 to 1 the energy drawn is CL VDD square, and so the total energy that will be drawn will be equal to CL VDD square into N. Now, what is the power dissipation, average power dissipation? That will be equal to limit n tends to infinity. For large value of n, we shall take an average En by f in En by n into f. F is the clock frequency. So, this value of En we can substitute here, and that will lead to limit n tends to infinity Nn by n into CL VDD square into f. this particular factor is given the simplified term, that is alpha. That means, this limit n tends to infinity n by n, this value is given the value given the symbol alpha, that is switching activity. Switching activity. Therefore, you can say that average power dissipation is equal to alpha CL VDD square and F, and that is the average power dissipation on the load capacitance CL. Obviously, this is not the only power dissipation that will occur, there will be power dissipation in the internal nodes. We find that there are various internal nodes, and here a 3 input NAND gate is given. So, here you can see in this 3 input NAND gate there are 2 additional nodes at this point between the junction of Q4 and Q5 and between the junction of Q5 and Q6. So, these capacitors also will get charge and discharge. So, for a generalized CMOS circuit, what is the switching power dissipation? P switching will be equal to alpha L CL. Alpha L is the probability of that switching activity on the load capacitance, alpha L CL VDD square F. Then it may have a number of internal nodes which is represented by I2, say maybe n nodes are there, I is equal to 1 to n, and you have to take summation of this power dissipation, that will be equal to alpha I into Ci. Ci is the node capacitance, alpha I is the probability switching activity at that node, into VDD into VDD minus VT, because in this case, as we have seen, we have already seen that in such situations, whenever you are charging and discharging this capacitor or this capacitor C1 and C2, it will not charge to VDD, but it will charge to VDD minus VT. That is the reason why you have used the expression VDD minus VT here. So, this is the switching power dissipation in a general CMOS circuit. Okay. Now, so far we have assumed that inputs are equiprobable. What do you mean by equiprobable? Say a particular gate has got 2 inputs A and B, that probability of occurrence we assumed is same, but it will not be true in real life. Some inputs will come from one source, another input will come from another source. So, or some inputs will be generated by a complex circuit. As a consequence, the inputs will not be equiprobable, their probability of occurrence will not be same. Earlier we assumed they are same, or we assume probability of occurrence is 1. So, in such a case, how do you calculate the switching activity? The probability of transitions at the output depends on the probability of the transitions at the primary inputs. So, we have to take into account the probability of transitions at the primary input. How do you take it into account? Let us consider a 2 input NAND gate. In case of a 2 input NAND gate, we know that P0 is equal to Pa into Pb. You know, P0 means what is P0 for a 2 input NAND gate? We have a 2 input NAND gate A and B. So, Pa is the probability that this node will become 1, probability of transition to 1, and Pb is the probability of transition to 1 for this node B. And you can see when the output can become 0, when both the inputs are 1. Therefore, P0 will be equal to Pa into Pb, and however, your P1 will be equal to 1 minus Pa into Pb. So, we find that that P0 is not is no longer 1 by 4, or P1 is no longer 3 or 4 in this particular case, because it all depends on the probability of transition to 1 and probability of transition to 0, that will be different. Therefore, P0 to 1, which is the that switching activity, which will be equal to P0 into P1 for a NAND gate, will be equal to 1 minus PA PB into PAPB. So, we find that whenever the inputs are not equiprobable, in this way we can find out the switching activity. And similarly, the switching activity of NOR gate we can find out that for a NOR gate it will be equal to 1 minus PA into 1 minus PB, probability of transitions to 0 and probability of transitions to 1, and you can multiply it. NOR gate, this is the situation. For XOR gate, it will be equal to 1 minus PA plus PB minus 2 PAPB into PA plus PB minus 2 PAPB. So, we find it is a little complex whenever we take into account the probability of transitions for different inputs coming from different sources. In fact, with the help of a simple NAND gate, if the output is coming from a NAND gate, we can find out the probability of transitions. For example, say we have got a NAND gate, and as we know the inputs may be equiprobable here, but here the probability of transition to 0 and 1 are not equiprobable. So, as we know, suppose this is when the circuit is in the 0 and this is when it is 1. What is the probability of transition from 0 to 0 for a NAND gate? For a NAND gate we know that 0 0 0 1 1 0 1 1, output is 0 only here. So, in this case these are 1. So, probability from 0 to 0 is 3 by 4 into 3 by 4. Probability for a transition from 0 to 0 will be 3 by 4 into 3 by 4. Probability of transition from 0 to 1 will be equal to, from 0 to 1 it will be equal to 1 by 4 into 3 by 4. Similarly, probability for transition from 1 to 1 will be equal to 3 by 4 into 3 by 4, and probability for transitions from 1 to 0 will be equal to 3 by 4 into 1 by 4. So, we find that probability of transitions to 0 1 at the output of a NAND gate is not same 1 to 0 and 0 to 1. That is the reason why this type of probabilities are to be taken into consideration. And in a complex circuits, that computation of switching activity is not very simple. However, it can be done the way I have explained. Now, there is another complexity in our circuits. Earlier we assumed that all the inputs are independent. So, if the inputs are coming from different sources and there is no correlation among them, obviously they will be independent, but in reality that cannot be so. So, there can be some inputs, I mean some input will appear, and again the function generated by it will converge with another signal. For example, let us consider a simple circuit. Here I have taken a 2 level circuit. Here it is a NOR gate, 2 input NOR gate with input x1 and x2, and here we have another gate with input x3 and x4. So, we find that the probability these x1, x2, x3 and x4 all are independent. So, the switching activity at this point will be 3 by 16. Similarly, the switching activity will be 3 by 16, and if we consider the output, the switching activity here will be 63 by 256. But suppose these two are tied together, then what will happen? Then what will happen the switching this output and this output are no longer independent. Here this is independent, these two are independent inputs, but here these two are not independent, and as a consequence here the probability of transitions will be 3 by 5 into 5 by 8, and as a consequence the switching activity becomes more 15 by 64, and in fact it can be illustrated with a more simple circuit. For example, we have a simple NAND gate. Now, in this case we have applied two inputs A and B, and as we know the switching activity here will be 3 by 16. Now, suppose what we do, we apply an inverter and apply to the two inputs. In this case what will happen? What will be the switching activity? So, in this case whenever this is 0, this is 1, and whenever this is 1, this is 0. So, what will be the switching activity here? And surprisingly you will find that since A and B, these two are correlated, the switching activity will be 0 here, because output will be always 0. As you know, in a NAND gate, whenever you apply any input any input 1, output will be always 0, the switching activity will be 0, output will be always remain 1. So, whenever you apply this kind of thing, that means in this type of whenever there is some convergent inputs, the convergent outputs are taken together, then the switching activity increases, and in this particular case we have seen it has decreased, that means it has become 0, switching activity is becoming 0. So, this type of this mutually dependent inputs you have to take into account when multi-level network of complex gates are considered. The inputs of a gate at a particular stage might not be independent. So, you have to take into account this in your circuits. Okay. With this, let us come to the end of today's lecture. We have discussed about the one very important sources of power dissipation, that is your switching power dissipation in CMOS circuits, and we have seen it is proportional to what parameters. You have to consider the important parameters on which it is depends, CL, load capacitance, or if it is internal load, CI, then it will dependent on VDD, and particularly we find that there is a square law dependence on VDD square, and also it depends on frequency. So, from this what is our observation? Our observation, why we are studying sources of power dissipation? Essentially we are trying to identify the enemies. So, here our enemies are capacitance, supply voltage and frequency. So, we find we can, if we want to reduce switching power, we have to reduce load capacitance, we have to reduce supply voltage, and we have to reduce frequency. So, later on whenever we shall discuss techniques for reducing switching power dissipation, we have to focus primarily on supply voltage, because the switching power dissipation heavily depends on supply voltage, and of course, the another parameter I did not mention, that is your switching activity. So, these are the parameters on which we shall concentrate, and we have to minimize or reduce one of these 4 parameters to reduce switching power dissipation. So, with this let us come to the end of today's lecture. Thank you.